So until that time, you know, we'll bring it up. But for right now, I'll get started here. I'll turn it over to Brian. Just a little bit about him. Brian has provided geological consulting services to the petroleum industry and mining industries in Canada since 1985. This includes the assessment of strata for their hydrocarbon-bearing potential and exploitation, particularly through the application of horizontal drilling methods. Since 2007, he's been, sorry, I skipped a little bit. Since 2007, you've been doing some assessment work, including the potential for mining geothermal heat from deep aquifers in Saskatchewan to be used in direct heating and industrial process applications. Recently, work has included in assessing the potential application of compressed air energy storage in Saskatchewan, which is the title of our talk today. So without further ado, I am going to turn over control to Brian, and I'm going to turn off my camera and we'll go from there. So Brian, I'm going to make you presenter, and perfect, we can see your screen.
Okay, am I in presentation mode on your side of things?
Absolutely.
Okay, that's terrific. So I'm always scared doing this to get started.
Yeah, no worries.
So thanks very much for inviting me to make this presentation. And special thanks to Shane for looking after all these technical things that we have to deal with this stuff. As Shane said, I've spent the last 2 years working on or investigating how compressed air energy storage could help develop our renewable resources more effectively, and in Saskatchewan. And I'm happy to just provide a summary of what I've discovered so far. So I'm going to provide a little bit of an outline here. I'm going to talk about SaskPower's planned inclusion of renewables into the grid, and the ways that we have, the potential ways we can actually start to decarbonize the grid in a significant way by advancing renewables. And of course, what's the important part about that is the converting renewables to firm capacity using energy storage. And I'm going to describe, in this particular case, how compressed air energy storage works. And again, the opportunity we have in Saskatchewan to use this technology, because we have abundant experience developing salt caverns. I'm going to touch on another side benefit of this, of actually storing heat in the deep subsurface. My background is, for quite a few years now, has been in geothermal energy, which is an attempt to extract heat. We can also use these aquifers for storing heat. And that's going to lead us into a little bit of a few comments on using the electricity from renewables to make hydrogen, which can then be used to make power in different forms, and how if we learn about a storage pathway for compressed air storage, how complementary that will be to the eventual development of hydrogen in Saskatchewan. So SaskPower's stated intention is to have 50% of renewables, 50% of generation capacity to come from renewables by 2030. And at that period of time, eventually abandon all coal generation except for the Boundary Dam carbon capture and storage plant. And by advancing the development of wind and solar generation, supported by additional gas generation capacity, the new Chinook plant at Swift Current, 350 megawatt plant that came online last November, I believe. And they have secured a 315 megawatt power purchase agreement with Manitoba Hydro. So where can we actually develop, what are our opportunities for developing low and zero carbon energy in Saskatchewan? We look at potential for more hydro, and of course there's very limited growth potential there, particularly in southern Saskatchewan. Pumped hydro, we have very limited potential there in Saskatchewan, again, particularly in the south where the need is greatest. We're investigating the potential development of SMRs. That technology is a few years away, and there are some issues in terms of load following, because we'll see how this unfolds, but they may have limited ramping ability, and we'll see why that's important in a little bit. And of course, there's a number of social license issues that will need to be resolved. Potential for more geothermal for energy generation. I'm sure, familiar with the Deep Earth Energy Project west of Estevan by the US border. It's early days for that technology. It's looking promising. We'll see where that goes, but it's still early days. There's a ways away yet before that could become reliable. And of course, we have carbon capture and storage technology that's been worked on in Estevan at the Boundary Dam project for many years. There may be some potential for expansion there. And of course, we have our renewable energy sources, which in Saskatchewan speaks predominantly of wind and solar. There's two maps of North America with Saskatchewan highlighted. And without getting into the details too much, the one on the left refers to the average wind speed at 100 meters height. And the one on the right is yearly solar output for solar generation, potential for solar generation. And you can see in the southwest quarter to third of the province, there is, as the colors warm, there is significant potential for the development of wind and solar in Saskatchewan. Over a large area of southwestern Saskatchewan. This is a picture of the Element 17 megawatt solar panel field near Brooks, Alberta. I recall driving by this a couple of years ago when I was kind of pleasantly surprised by the size of a project like this. Costs for solar, this is in the news lots, of course. Costs for solar and wind continue to drop significantly. SaskPower is reporting that they will have 60 megawatts of solar generation will be added by 2021. But really, this really kind of speaks to the thousands of megawatts additional potential for solar development in the province. Similarly, for wind, this is a picture of the proposed 200 megawatt wind farm near Assiniboia, where wind prices are predicting around 3 cents a kilowatt hour in 2025. And I think we may actually be closer to that already. As of the end of last year, there was 241 megawatts operating and an additional 387 megawatts that have been approved. But again, these are really tiny numbers. We have the potential for thousands of megawatts of additional potential between our renewables. And I'll use the word renewables. We'll be speaking mostly about wind and solar, but it's just really a proxy for all potential renewables. Wind particularly has the greatest capacity and potential in Saskatchewan. This is a wind profile chart from two fields, Bull Creek and Wintering Hills in Alberta. We can use these again as a proxy in Saskatchewan. These are located in east central Alberta. Representing the first week in January of 2017 and the first week in June. And this chart really just goes to show the difference in generation profiles at different times of the year and at different times of the day. That really just speaks to the intermittence of the intermittent behavior and spiky behavior of wind generation. The profile is somewhat predictable, but it's still very intermittent. And it's intermittency that is the largest issue we have to deal with when we consider developing or trying to include, again, renewables into the grid. So, and it's because of this intermittency that energy storage is required in order to smooth that electricity over the fluctuating demand periods. And so really to facilitate that large-scale development of renewables, large-scale energy storage systems are required. This is a picture of the Adambeck hydro site, built in 1957. This is a pumped hydro, or Canada's only pumped hydro facility. This is a closed-loop water system. Pumped hydro is the largest form of energy storage worldwide and has been for decades. We have this one project in Canada The storage is very flexible, large scale and long term. These are just wonderful assets to have, but the location is very significant. And I can't imagine we really have any suitable locations in southern Saskatchewan, particularly. There are a few sites being considered in the eastern slopes of the Rockies in Alberta and into BC, but nothing available really in Saskatchewan, at least in southern Saskatchewan. This is a picture of something quite close to home. The CAES's combined wind and solar energy facility near Regina, where there's a small solar field and a single wind turbine generating electricity. And there's a battery pack on site. This project's been managed by SAS Research Council for many years now, and has been quite an exciting history. So it shows the potential as a small demonstration project how we can actually store renewable power that can be then dumped into the grid at the appropriate time of the energy cycle, the generating cycle. This is scaling up things quite a bit. This is a 100 megawatt power pack system in southern Australia, where wind energy is stored in these giant power pack systems built by Tesla. Batteries can provide complementary short-term duration. They're wonderful, and they have a rapid ramp rate. They can be turned on and fired right up to capacity at a very short period of time. This is important to follow load. The life cycle for SIMP batteries is simple. It's really a charge, discharge, and recycle. It's a chemical storage technology requiring minerals and metals, of course, for mined products. And ancillary to that is the mining of waste must be considered in the development. And again, it's suitable for short-term storage, really measured in hours. Although technology costs per kilowatt hour are improving, market and geopolitical risk acquiring raw materials are less predictable, and these are becoming much more newsworthy these days. As we look at foreign markets for accessing this material, and in terms of cost, eventually the cost of batteries it'll probably not be much more than the cost of raw materials as the technology improves with time. So how does CAES work? How does compressed air energy storage work? I'll see if my mouse is on there. Yes. We have wind and solar generation. Both of these supplies can go directly to the grid, but any excess sun and solar and wind generation can be used in a compressed air, in an air compressor, and pumped into, using atmospheric air, can be pumped into a salt cavern that's been built specifically for this compressed air storage. At a later part of the generation cycle, this air then can be released in a controlled fashion and be run through a turbine, on-site turbine, to generate power that is then put into the grid. It's a very simple process. There's no chemicals involved, and there's no toxic waste, and we're just using atmospheric air. At the yes, we'll go from there. It's a very simple process. This is not a new. The plant picture on the left is from Huntorf, Germany. It's a CAES facility. It was developed in 1978 and is under consider for expansion now. A 290 megawatt system. And in 1991, the plant on the right is from McIntosh, Alabama, 110 megawatt system. So these plants have been operating over 70 years combined, and with very reliable production on time, very little downtime. They've been very successful units. So compressed air energy storage will help to smooth the power provision from intermittent renewables, and thereby convert renewables to what's called firm capacity, which is providing flexible, large-scale, long-duration storage that eventually can actually emulate base load. It's this firm capacity that is comparable to what a natural gas fired facility might produce. So in this graph, this is a 24-hour period in the day where I'm trying to show what baseline would look like. Baseline is the baseline power is the minimal power produced all the time. That's the minimal amount of electricity that's produced on a 24-hour basis. And this base load line is provided predominantly in Saskatchewan by coal electricity generation, supplemented with natural gas and some hydro. The renewables fit in there as well, but their role is very tiny in that capacity right now. But I think predominantly of coal. Coal plants are not very flexible in terms of their ability to ramp up or ramp down. So they do a lot of the heavy lifting with base load. The grid demand, the brown checkered line, is represent what the actual load demand is, and you can see it changes throughout the day. That's a fairly gentle curve, but that actual grid demand is variable from hour to hour and minute to minute, and it's SaskPower's work to follow that, to do a load following, and they meet that by ramping up and down our hydro assets and our gas generation assets to try and just fit right within that dashed line. So if we lay over that system a solar energy provision, you can see how and again, this is a proxy for solar and wind. Solar is easy to see here because it's nice and yellow. You can see that there's the portion at the bottom where the solar is actually providing a portion of base load. And in this section here, underneath the dashed line, it's providing a portion of the grid demand. But it's because of its intermittent nature and the scale at which is available, there are sections here that it is unable to cover, like on the shoulder period, where in this case the sunshine is not available. And also we also have in some cases, it's hard to imagine, but this is a common occurrence in more mature renewable markets like California, Ontario, and even Alberta has some problems with this, where we have actual excess solar generation. And so what can we do with this electricity that's generated? We have these assets in place, and in many cases, this actual production is curtailed. It's actually the wind turbines are actually the generation stops because there's nowhere to actually send that electricity. So instead of curtailing that electricity, if we take this extra electricity and use that for compression in a compressed air energy system, and forward that storage to the next day, we've actually smoothed that. We can actually let that energy, we can release that compressed air and follow that grid demand. And we thereby smooth that power provision to follow the grid demand. And we've replicated what a natural gas generating system can actually do. As we develop our renewable resources even further, they can begin then to contribute to actual base load with the same principle. So I'm going to talk a little bit about geology now. I'm going to try to illustrate very simply how caverns are developed. This is a very stylized stratigraphic cross-section right across the province, where we have the large pink section here representing our prairie salt. In a very large part of the basin, we also have stringers of potash at the top. And depending where we are, more in this, around Saskatoon and in the southeast, there are presence of Winnipegosis mounds. And of course, within this large salt section, there are also often stringers of anhydrites and insolubles, things that would be we would try to avoid when developing a cavern. So following a 3D exploration program to find the ideal conditions for cavern development, the process would be to drill a first well and core the salt to assess its mechanical stability features and its dissolvability of mining properties, those kinds of things, and its stability for mechanical stability for cavern development. So once that's been satisfied, it just would be a matter of a solutioning mining process, as many I'm sure are familiar with, is as simple as, not as simple as, but using fresh water to wash the cavern space. And that's enlarged using specific mining methods, of course, that we've learned over years since the mid-1950s, how to control the size and shape of that cavern that's been developed. Of course, in itself, we can create these caverns, but another feature that is also necessary is an aquifer where we can we have to be able to dispose of that brine. For every unit of salt that's dissolved, I think there's been 3 and 5 units of brine that's been created. This is very salty water, of course, so it has to be dealt with appropriately. It can't be left on surface. So in the Belle Plaine area up through Saskatoon, the Deadwood Aquifer is used as a disposal location. And in the west central part of the province around Lloydminster, the Lower Manville is used for a receiving aquifer for that salt. So of course, once this infrastructure in place, additional caverns can be created. We have excellent geological and cavern operating conditions for CAES in Saskatchewan. The optimal depth for a CAES facility is between about 800 and 1,200 meters depth. They can be developed deeper than that. I mean, there are caverns at Regina as well, which are quite a bit deeper. But the efficiencies change because with greater depth, the salt is there's greater temperature, and salt is more plastic at greater temperature. There's potential for flow within the salt, so the pressure has to be maintained at a higher level as we get further south and deeper salt. So it changes the pressure profile that's available for the air being compressed and extracted. We have the disposal aquifers available for brine. There's been lots of work in Southern Ontario and New York State for developing CAES facilities. They have suitable salt, but there's issues around no suitable deep aquifers to dispose of it. The operating range is from 6 to 20 MPa. And in Saskatchewan, we have abundant experience with cavern development, of course. I think the first cavern at Melville was in about 1958. This is a map of the prairie salt distribution throughout the province. It covers a very wide swath of the province, of course. This is a profile across a section with Saskatoon in the center. What I'm trying to show is the 800. There's an 800 to 1,200 meter. Again, this is just the ideal depths for CAES development. The contour level to show the kind of the optimal depth locations, and you see there's a very broad corridor right from Yorkton through Saskatoon, North Battleford, and Lloydminster in terms of depth. And of course, we want to develop caverns as large as possible, depending on what the load will be, of course. And so this is an isopack of the thickness, the total thickness of the salt. And you can see from the warmer colors represent thicknesses up to 200 meters of thick. So that's quite a bit of salt that we can actually work with. So what I've done here is mask the two. So this the magenta color shows the area with the ideal depth between 8 and 1,200 meters and salt thickness over 120 meters thick. And again, these are just kind of ideal physical locations. It's by no means restrictive to go into other areas where the salt's suitable. But you can see there's a very large corridor with a number of large urban centers that could utilize these facilities. This is an image, a sonoware image of one of the Transgas Asquith wells, caverns just west of Saskatoon. It has an average depth of 1,140 meters and is about 5 million cubic feet in volume. So this is a moderate-sized cavern. So I'm going to get into a little more detail about really two compressed air energy storage systems. The diabatic system, and the diabatic means the heat that's generated from compression at this point here, when the compressors are operating on the renewable electricity source, there is an enormous amount of heat created, and that heat is just released to the atmosphere. But we have the result of the compressed air now in the cavern. When that later in the power production cycle, when that atmospheric air is released, when it goes into the turbine, there's a modest amount of natural gas is included with that, and that's combusted with the air, with the compressed air, to provide some immediate heat for expansion. And that expansion, of course, is what's going to really provide a lot of power to that turbine before that electricity goes into the grid. So there is a relatively small natural gas input at this point. This kind of a system would be essentially the same as what's happening in the Germany, the Huntorf and McIntosh, Alabama projects. What's not, or the next, there's another opportunity here for Saskatchewan, and that is the adiabatic system. And the adiabatic just refers to that heat is actually stored and reused. So instead of that air being lost during compression, it is actually stored by a recuperator of some kind. That could be on-surface storage as well, with large recuperators. And so what happens now is when the air is released when the air is released for generation, that heat is then added at that point. And so this system no longer uses any natural gas. This system is 100% carbon free. There is no combustion involved with this system at all. The operating costs are higher, but the basic CAES system has the capacity to operate with zero greenhouse gas emissions. So in this case, we've used renewable sources. We've converted intermittent renewable sources into firm capacity with zero greenhouse gas emissions. So as I mentioned, the amount of heat that's captured is very large. And this is a stylized diagram of how, once again, our geology we're lucky enough to have this wonderful geology to be able to capture this heat from compression and actually inject it into manville aquifers, near surface aquifers. And once the appropriate area of aquifer is heated up to a sufficient sustainable level, then during the expansion stage, that heat can then be recovered. That captured heat can be recovered. And it's because of that system we can now eliminate the use of natural gas and generate zero carbon dioxide. So the consideration of geostorage in heat and subsurface aquifers is another Saskatchewan advantage we have here. So CAES is an excellent storage option in Saskatchewan. It's quite a small surface area, and as all the storage is underground, it's a reliable, low-cost replacement for coal. I think that CAES can effectively replace all coal generation in Alberta and Saskatchewan. This technology would employ highly skilled industry trades, scientists, and engineers, and provide some opportunities for oil field and power utility operators that are going to be transitioning in careers, and provide opportunities for geoscientists and engineers and energy development. Our regulatory infrastructure is generally in place already. We're not in the adiabatic CAES system. There's nothing being combusted. We're using atmospheric air, and there's no toxic wastes. And in this case, no legacy disposal or reclamation issues. And we have high quality, excellent geological sites. Wind is our greatest renewable asset right now. So if we are more specific to wind generation, because it's available all year round in a large way, Wind plus CAES in Saskatchewan provide that a flexible load following capacity that we've seen. And it converts intermittent renewables to firm capacity, eventually even emulating base load. With suitable storage, CAES will facilitate large-scale renewable generation development, potentially replacing the construction of more natural gas plants. And a new diabatic system, that's the one where heat is not captured. Right now, it's cost equivalent to in-class combined cycle gas turbine generation, like at the Chinook plant at Swift Current, with an 80% reduction in greenhouse gases. This is provided to me by an energy developer in Calgary called RMP Energy Storage, who are interested and are in the early stages of designing a system to actually build in Saskatchewan. So this is, again, cost equivalent with an 80% reduction in greenhouse gas emissions. And of course, having a CAES facility where we have these large caverns, we can actually start to integrate large-scale hydrogen storage, as well as hydrogen can be added as an additional fuel, a supplementary fuel with natural gas. Just going to touch on hydrogen for a moment, where we use hydrogen to we use electricity to create hydrogen, to then create power in its various forms through fuel cells. We can use renewables to make green hydrogen using advanced electrolysis. And natural gas, we will be diverting natural gas through this kind of a stream because we're trying to avoid the combustion of CO2, but we can actually use we can reform natural gas to create what's called blue hydrogen, which still produces carbon dioxide, but when combined with carbon capture and storage, there is an opportunity to then use our natural gas converting to hydrogen and then capture and dispose of the CO2 emissions. And we have the potential for storing hydrogen in salt caverns, possibly at the same facility as air and natural gas. Using salt caverns for hydrogen storage is suitable as well. The mechanical properties of salt are stable, and salt in itself is inert with respect to hydrogen. And as it can be a problem, but salt is also, because of its plastic properties, it can be self-sealing in terms of leakage in some cases. Salt has very low permeability compared to other geological media, and of course, caverns can provide very large volumes for storage. Most hydrogen is stored on Earth in metal containers, of course, and there's a real issue with steel with hydrogen, as it causes embrittlement in metal. And there are currently 4 hydrogen storage facilities in the world, 3 on the Gulf Coast in Texas and 1 in northeast England. So they're not widespread. I mean, a lot of conditions have to align in order before we can even make caverns for anything. So this is a kind of a stylized idea I have for an industrial complex to use our CAES to create a CAES asset that can then be expanded once that surface infrastructure is in place. The size can be increased incrementally. As opposed to battery storage, to increase battery capacity, it's more of a linear cost where you just have to add more batteries. Where in a CAES project, where you can you have the opportunity of magnitude scale, and you can use a lot of the existing surface infrastructure. We could have natural gas on site, and we could have hydrogen on site. So you can see there's the potential to combine a lot of different industries within this, with CAES providing the fundamental groundwork. Some summary points that are important to consider. I mean, for me, is the timing. Renewables are available now, and CAES technology is available now. We have lots of operating experience. People know how to build and run these things. We can build CAES facilities instead of more gas turbine facilities, thereby allowing rapidly increasing the generation from renewables rather than hydrocarbons. Wind plus CAES is cost effective. Again, it's equivalent to gas turbine generation now with 80% fewer emissions. And so it's, for me, there's the benefit of reduced emissions, but this is just good business. And an adiabatic CAES system has 0 greenhouse gas emissions. It costs a little bit, it's more expensive, but there's the potential for that as well. And incidentally, when I refer to the wind plus CAES being cost equivalent to combined cycle gas turbine generation, that does not consider the added cost of any kind of a carbon tariff or tax. This is before any kind of a tariff. And of course, CAES can provide an operational platform to include hydrogen as fuel, as we all want to get on board to help develop Canada's hydrogen pathway. It's just a ways out there. And the conditions for CAES in Saskatchewan are exceptional. There's so many things line up. We have unlimited wind and solar resources. We have abundant salt cavern potential locations. We have excellent brine disposal potential. And we have this excellent capacity for heat geostorage in the case of an adiabatic system. And we have a highly trained and qualified workforce. So with that, I'm happy to open up a discussion and answer some questions as best as I can. Thanks.
Well, thank you, Brian. That's been a very, very interesting talk. I don't think a lot of us knew, some of the potential for these alternative kind of energy methods, especially when it comes to storing it. You think so much of just batteries, but to have, a natural almost storage ability to store, this green energy, I think that's really, really got some really good potential for this whole province. So right with that, I am going to take off my sticky note and unmute everyone here, so that if anybody wants to ask you a question, they've now got the ability to kind of open the floor here to anything. Anything. I think there's a first one here just in the chat, Brian. I will read that to you if you can still. Oh, I think I muted you by accident there, Brian.
Okay.
So the first one, just in the chat from Tabitha, what are the energy costs compared to geothermal?
I'm not sure that's very easy to answer, especially for me. It's going to be tough to compare those two because the energy costs are from renewables. That's the source of the electricity, is probably 3 to 5 cents a kilowatt hour, whereas the energy cost from geothermal is I don't know what that is. We don't know what that is because we don't actually have one operating. But on a larger scale, I guess you'd have to look at a levelized cost of performance for the two sources, and I'm not sure I can try to go there. But we know that renewables are relatively inexpensive. And they're getting less expensive all the time. Like that, around that 3 to 4 cents per kilowatt hour is, I think it's the lowest source of electricity being generated anywhere now.
Thank you. It appears that the ideal wind potential in Southwest Saskatchewan, whereas ideal CAES is centrally located east of Saskatoon. Is this an issue?
No, I don't think so. No, it's not really an issue because the Saskatchewan grid is very well interconnected. So you can actually bring in the renewable source from anywhere because it's all tied into the grid. What's more important is where the CAES facility is located. Because you're generating a large amount of power, like 150 megawatts or larger, it's ideal to have the CAES facility located at near the load, so just outside of a city, right near Saskatoon or Regina or Lloydminster, for example. Otherwise, would probably be a requirement or a need to build additional transmission infrastructure. So they don't have to be close to the supply. They have to be close to the load.
Excellent. Sorry, I clicked a button and I might have muted everybody there.
I have a question as well.
There we go.
I worked at the salt plant in Unity, which is a couple hours west of Saskatoon, and I know they've got a natural gas cavern storage facility there. I'm a little surprised with the amount of caverns we have available and the interest in this that it hasn't been tried. Have they actually pushed this idea forward a few times, Brian? Like, it seems relatively straightforward, and it seems like there'll be readily available caverns and infrastructure in place to actually give this a shot. Have they done any kind of testing on that?
No. There's a few concerns there, Darcy. For one, if a cavern becomes available, I would guess that's because it's no longer suitable, because they're very valuable assets, of course. So they might be leaking, for example. If they're no longer useful for gas storage, they may be leaking. The other thing is the size of the casing would probably be too small, so it would require drilling a new well, because the casing has to be like 12 or 13 inches in diameter. The casing for a gas storage well might be 7 inches or something like that. There has to be a high volume capacity. That might be another issue. It's we don't really have need for storage, large scale storage yet. So it's kind of cart before the horse. I mean, when Huntorf and McIntosh were built, they were to help satisfy load leveling tied in with nuclear energy production plants, where they like to run at a flat line. So they were essentially making too much electricity at night and not enough during the day. So they happened to be sitting on salt where they developed this technology. So it helped them to load level. Whereas now, because of that experience, the focus is now on renewable generation, which is intermittent. So this provides that storage opportunity and that load leveling with renewables. So it's kind of being reapplied for different reasons. There's a number of places in the world that are looking at this, but so far there's just those. There hasn't been any new facilities built in salt caverns in 40 years. So the focus is different now. So I think it's part of the conversation, becoming more of the conversation. I mean, I've spoken to SaskPower about it. They know about it. They have an interest in it. I think they're still undecided whether they need long-term storage or not. Maybe the focus is on batteries largely. But the potential for CAES development is very unique to the geology. And that's why this is so important to Saskatchewan, and Alberta for that matter, is that we have the suitable geology for it. Not that many jurisdictions have that ability.
I see, Tabitha, you've raised your hand. I'll come back to you just in a minute. I see there was a question from Dan. He said, I imagine that compressed air alone is enough to drive the turbine. Why is heat required from either heat storage or natural gas?
Think about it like a turbocharger. If you add a small amount of natural gas as that compressed air is, like if you think about how a turbine works as well, it's actually a compressor as well. So by providing, it's a compressor with natural gas, and it's the spinning of the turbine that creates the pressure, which it will do with the compressed air. But the combustion of gas at the same time just provides an amazing power boost because it causes that air to expand further, which is what you want, that I guess extra horsepower, I guess you could say. So it makes it so much more efficient by adding a little bit of gas. So that heat component is very important.
Excellent. Tabitha, if you had a question, I'll let you go now, and then we'll go to Dave's question, and I might leave Dave's question after this one as the last one.
I just wanted to add a bit to what you had said, Brian, about the suitability of other caverns. And like you said, they're not built to do CAES, and that anhydrite, the shell anhydrite is usually a challenge for the solution mining. So it doesn't create a beautiful cavern like you showed in your presentation.
Well, they're all very site specific, aren't they? I mean, that was a very, very generalized profile, but that's the value in doing that. That's do the appropriate exploration work to find the optimal conditions. And of course, there was ways of trying to break down those anhydrite stringers as well. So, yeah, that's part of the process of good cavern development. But we have lots of experience of doing it, so it's taking advantage of that knowledge that we have here in Saskatchewan to do that.
Cool, thank you. Dave, do you want me to read your question, or do you want to ask it?
I can ask it. Is my mic on now?
Yes.
Okay, I presumed it was. Yeah, Brian, kind of had a few questions dancing around the economics of this so far. It's a pretty elegant story. I've heard you give this story before. There was a few more nuances this time. It makes a lot of sense, but are there any companies out there actually looking at, sort of preliminary economic studies or pre-feasibility studies just to understand what are the capital costs, what might be the operating costs? Are there any actual numbers people are looking at for these sort of operations?
Yes, there are. I mean, and the one company that I've been in contact with to get most of the information, a lot of the information I have is called RMP Energy Storage in Calgary. And if this is a good reference point, they're kind of at the pre-feed stage of a project development. And their work has suggested that they can generate full-time zero carbon electricity for about $100 a megawatt hour. And that would be an adiabatic system with heat utilization, heat capture and utilization. A diabatic case system where it generates 80% less of a combined cycle gas turbine system would be about $70 per megawatt hour.
Mm-hmm.
So yeah, they've done a lot of work in modeling on this. So to the confident level where they're entering a pre-feed stage.
Okay. Do you have any idea what the actual, say, I know would depend on the size of the operation, but what the capital cost, if you had to create your own cavern and set up all the surface infrastructure, what would be the capital cost we'd be looking at?
I would throw around between 600 and 800 million. So it's about the same as a new CCGT, combined cycle gas turbine facility. It's it's in the same neighborhood of cost.
Okay, thank you.
As kind of the gross capital cost, and of course the cavern development, we're talking $5 to $10 million, I suppose, per cavern, depending on how many would be constructed. So it'd be that $700 million mark around there.
Okay, thank you.
All right, I think we'll stop questions there for now. Normally, Brian, when we do this in person, we get everybody, we give you a round of applause and present you with a speaker's gift on behalf of the CIM, Saskatoon Geosection. Obviously that doesn't quite work right now, so after this I'll have to get your your mailing address and I'll ship you out our little speaker's gift. But just on behalf of the CIM Saskatoon Geosection, just thank you for taking this time to give this talk.
You're very welcome.
Yeah.